So let's suppose we want to build a circuit that divides an input clock by 3. So we can see here we've got a clock line that's toggling, and we have 3 outputs, Q1, Q2, and Q3. On the positive clock edge of the clock line, whichever input is currently turned on gets turned off, and the next one turns on. So at the start, Q1 is high, and Q2 and Q3 are low. Positive clock edge occurs, Q1 transitions low and Q2 transitions high. And then on the next edge, Q2 goes low and Q3 goes high. And then on the next edge again, Q3 goes low and Q1 goes high. So in a sense, you can consider this circuit as kind of like a division by 3, because for every positive edge of the clock, we only get one positive edge out of every 3 for each of the output signals fixtures. So Q2 has a positive edge here, and then it skips 1, then it skips 2, and the next positive edge is 3 clock cycles down, and the next positive edge would be 3 clock cycles after that, and sort of so on and so forth. So this circuit essentially can be used to divide the frequency or the number of positive edges by 3, and by looking at the output of Q1 or Q2 or Q3, you can tell what state it's currently up to. So this would be useful for like sequencing a set of actions. Maybe you could imagine Q1 is like the red on a traffic light, and Q2 is the yellow, which doesn't show up very good on my screen. Maybe we'll use amber instead. And then Q3 can be green. So this is actually in the wrong order. If Q1 transitions to 2, well, after green comes yellow, or orange in this case, and after orange comes red, and then red transitions back to green. So this could be used for like sequencing, particularly like a set of traffic lights. And then each positive edge, it transitions to the next state. So there's 2 approaches we could use to this. We could use a ring counter, or we could use a binary counter with a decoder. We'll cover both options, and then it's really up to you which you prefer. So the binary counter option was 3 states here, and to record 3 states, well, I need at least 2 bits, because 1 bit can only keep track of me being in between one of 2 states. So we need some sort of binary counter, which will be implemented as 2 flip-flops, because each flip-flop stores 1 bit. So here are my 2 flip-flops. D and Q are the inputs and the outputs, and they share a clock line, so they will get updated synchronously. There we go. So I have 2 bits here. We'll call this maybe state 0 and state 1. I want to somehow work out what should the new states be for the inputs. So S0 and S1 together represent a 2-bit number. So what I want this thing to do is go from state 0 to state 1 to state 2, and then transition back to state 0. On every clock edge, it'll switch between a state. So that means we can sort of draw a truth table for what we want for given the previous state, what should the next state be. So we've got a truth table. If the current state is 0, then I want to go to state 0, 1. The current state is 0, 1. I want to go to 1, 0. If the state is 1, 0, I want to reset back to state 0. And if the state is 1, 1, well, that should never happen, so I don't really care what the circuit does. And then from this, I can easily draw a schematic, right? The new value of S0 is the NOR of S0 and S1, something like that. So we can just add a NOR gate for the new input to S0. Let's just get rid of that, that's better. And then what should the new input for S1 be? Well, it's only 1 when S0 is true and S1 is false. So we can add an AND gate, and then negate the input for S1, which is going to be this wire here, and then don't negate the input for S0. So this gives us a binary counter, and these 2 bits tell us what state we're in. And then from there, we can just use a 2 to 4 decoder to basically take those 2 bits and represent it as one of 4 different options. So a 2 to 1 decoder can also be thought of as like a demultiplexer, where the input is always 1, the current state tells us which to choose, and then we have 4 outputs. That'll be our Q1, Q2, Q3, and then this last one, which we never get, is disconnected. So from this schematic, we can now build something in digital. And to do so, we're going to need 2 flip-flops. So we're going to use D flip-flops. We'll have 2 of them in parallel. Really, you could also adjust this thing to be a 2-bit flip-flop and then have splitters in and splitters out, but I think it's more clear to sort of draw them separately. Then we have our 2 state lines. So the top one is S0 and the bottom one's S1. So then we have to add the gates that perform this operation. So we have a NOR gate on the top leading into the new input for D. And then an AND gate with one of the inputs negated for the bottom input that represents the bit S1 in our state. So we negate the first input. There we go. And then we just have to route the signals around. So S1 is the inside signal. And then S0 is the outside one. Let's just check that matches the diagram. Indeed it does. We need our clock line. So we just add a clock component. It's always good to label it. And this will interface with both the clock lines and the flip-flops. And then we need our decoder component. This is something we could build from scratch, but there's also a built-in decoder. So it takes 2 bits, and one of these 4 inputs are high, so we will need a splitter for that. So if we look in the splitter component, there we go. So we combine the 2 bits together. The bottom flip-flop is the first bit, and the top flip-flop is the 0th bit. And then from our decoder, we can output some outputs. So we have our first output, which is Q1. So we'll label that as such. We have our second output, Q2, and then Q3. And we'll have to shift this over a bit to make it fit. Clean this up a little. Alright, that'll do for now. So how can we check the timing diagram of this? Thankfully, there's a component for that. If we go to I/O and add a data graph, this will basically plot the trace of all the signals, so we can check that this matches this diagram here. So if we start the simulation, by default, the flip-flop's initialized to 0, so we're in state Q1. On the next rising edge of the clock, Q1 falls, Q2 rises, because we transition to the next state, and stays that way. And then the next positive edge, we transition to Q3, next positive edge back to Q1. So we can see we have our divide by 3 circuit that cycles through Q1, Q2, and Q3, which is exactly what we wanted. So that's one way to do it. What's the alternative way to do it? So instead we could build a ring counter. So it's basically a bunch of flip-flops, each connected to the next, and the last one connects back to the first. So if this flip-flop was turned on, we'd have a 1 at Q0, and the positive clock edge, the 1 sort of move along to the next, and then move along to the next, on each positive clock edge. So we can build this thing in digital, and let's see what happens if we do. So the problem with this design is that by default, flip-flops in digital start at 0, so we're in the state 0, 0, from which nothing will ever change because each flip-flop has a 0 flowing back into it. Worse still, if you're using real flip-flops, it's kind of not guaranteed what configuration it would start up in, because inside a D flip-flop is an SR latch, and when you turn it on for the first time, it's in an undefined state. So this means we can't really start one of the flip-flops as a 1, and the rest as 0 to sort of get the pattern moving. So what we need instead is we need a different kind of flip-flop, so a D flip-flop with asymmetric inputs. So this is a kind of flip-flop that also has access directly to the SR latch that lives inside, so you can set or clear it asynchronously rather than when the clock line would occur. So what we need to do is to use 3 of these flip-flops instead. So we again hook them back to back, so each Q flows into the next D. This last Q wraps back around. And then we need to have an additional pin, a reset pin, that puts the circuit into a known configuration. So when we want to reset it, we want the first flip-flop to be 1, so we'll hook the reset to the set pin, and we want all the other ones to be 0. So we'll set the reset input into the clear pins. The last thing I'm going to do now is to hook up the clock line. So that goes to the clock on every input, and then hook up our outputs. One last note, of course, is that in digital you cannot have undefined inputs, so we need to feed a 0 into the unused set and control lines on the flip-flops. So when we start the simulation, the the flip will start at 0, so we can use the reset line to asynchronously set the flip-flops, and there's a typo there, so that Q should connect to the output, and that Q1, that should connect to the output there. Yeah, that's better. So we hit the reset pin, we reset the circuit into a known configuration, and then by toggling the clock, the ring counter sort of shifts the bit along, so each flip-flop moves the bit to the next, and we get the same intended behavior of our like traffic light as earlier. So there's trade-offs between both these options. Sort of the first one's a bit more difficult to design, especially if you had more bits, because then you have to work out a circuit that takes each bit, moves it to the next. Though I guess a general version of this would be you'd have each flip-flop route into an adder, so you get +1 for the next state. Whereas a ring counter, if you wanted like 10 different states, you need 10 different flip-flops, which can get quite expensive quite quickly. So the binary counter approach, I would say, is probably preferable and certainly more efficient.